All right, so let's talk about vector valued functions, and in particular we'll talk about curves in higher dimensions. And so basically a vector valued function is just a function from the real numbers into two-dimensional space, or the real numbers into three-dimensional space, or even more generally than that, we can go from the real numbers to n-dimensional space. So curves really inherently geometrically are really just one-dimensional objects, and so anytime to kind of capture that, the domain is really just going to be some subset of the real numbers. So the real numbers just being a one-dimensional real vector space, and so that's kind of where we get the notion of a one-dimensional object. Each component of one of these vector valued function is just then going to be a parameterization of some particular variable gamma. That we would have some function x is a function of t, y is a function of t, and z is a function of t. The domain of a vector valued function is really just going to be the intersection of the domains of all of the component functions. So if we had some function gamma being square root of t plus 1 in the I direction, 1 over t minus 2 in the j direction, and natural log of t in the k direction, then if we want to plug a value in for t, it has to be a value that will work in each one of these component functions. We can't have one that doesn't necessarily work. And so if we look at the domains for each one of the individual components, we see that the domain for our square root of t plus 1 is just going to be from minus 1 to infinity. The domain from 1 over t minus 2 is just going to be everything except 2, and the domain for natural log is just everything positive. If we kind of draw those out, kind of graphically illustrate them, then we've got on all our number lines, we've got some minus 1 to infinity for the domain of our x component. The domain for our y component is everything except 2, and the domain for the z component is everything positive. Well, if we just kind of look graphically at where all of those overlap, we see that with the z component we lose everything to the left of 0. We also lose 0 for the z component, so we can't have him, but we have everything in between 0 and 2. All of those values work, and then we lose 2 because of the y component. Then we have everything over greater than 2 that will work for all three of our component functions. So our domain for this vector valued function is just going to be from 0 to 2, the open set from 0 to 2, union with the open set from 2 on to infinity. Now, when we're talking about the graphs of curves, what we really mean is a graph that is returned is going to be the position vector to a particular point on the curve. So whether that's in 2 dimensions, we've got this position vector where the base of our position vector is at the origin, and it goes out, and the end point is going to be the actual point on the curve. So it works for 2 dimensions, it's going to work for 3 dimensions. What else we get with these curves is that we get kind of an orientation that goes along with them. We don't just have the image being the curve itself, we also have an orientation that is kind of extra information given by the parameterization. So if we just take a curve cosine t sine t, well, that's going to easily satisfy, we can see that satisfies the equation 1 is equal to x squared plus y squared. If we plug the value in for x, plug in the value in for y, it matches our trig identity, and so yes, this is really going to be the image of that curve. And so if we start at 0 and then increase as different values of t, so gamma of 0 is going to start us over here at 1, 0. At pi over 2, we're up here to 0, 1. And if we just kind of keep that going around, we see that we're actually tracing this curve out, our unit circle traced, counterclockwise, with a counterclockwise orientation. Now, if we just want to reverse the orientation, well, all we'd have to do is introduce a new parameterization that kind of goes backwards. So one way of doing that, at least for in this case, is that we can just throw in negative t. So if we have a new parameterization phi of t, well, that's going to be gamma of negative t, well, we have cosine of negative t, sine of negative t, then using our odd and even properties of sine and cosine, that just becomes cosine of t negative sine of t. And our domain is still 0 over to 2 pi. Now if we look at kind of how those values are put in, if we put in 0, then we still start at the same place at 1, 0, but then we throw in pi over 2, now we're down here at 0, negative 1 instead of 0, 1. So the effect that this has is that we trace out the curve in the opposite direction, and we actually have a clockwise orientation.